Hi, Stephen Neshaba here again, and I'm here to help you out with another part of the climate modeling Excel exercise. Now, the idea on this part here is that we've added an atmosphere, an isothermal atmosphere around the planet, and the physics of this is that we still have this shortwave radiance coming in, I1, it's the same as before. We've got I2 coming off, that is to say it's the Earth acting like a black body radiator. But now what happens is that some of that energy, that long wave energy, gets captured by the atmosphere, and then the atmosphere also radiates down and outward to space because it is itself a gray body. So now to implement those things, I recommend that you go into VDesk and Excel and set things up kind of this way. You'll see that I've added some more fields here. There's our old that's the solar constant, albedo, and the sigma. And now this is the absorptivity or emissivity, which we just need one box for because, well, according to Kirchhoff's law, that's the same number. And then we'll fill up some more of these boxes when you come back. Okay, now assuming you're back, we have a temperature. We have a field for the temperature of the planet, and we also have a field for the temperature of the atmosphere. And just for starters, I'm just going to arbitrarily put in a couple different numbers there. Now, I1, remember that's this incoming radiance. Now, I1 is just the same as what you did for the bare atmosphere free case. That's that. But if you want some practice on entering things in without any guidance, and go ahead and then press resume when you're back. Okay, assuming you're back, I1, that's the solar constant times 1 minus alpha. So I, as usual, start off with an equal sign, solar constant, star for multiply, times 1 minus the albedo. Okay, there we go. And I2, that's also the same as before. That's just the Stefan-Boltzmann emission from the planet surface times 4. Why don't you go ahead and give that a shot? Okay, I think what I need to do is to say that I2 equals sigma, which I have right there, times the temperature. Now remember, we've got two temperatures here. The temperature of the planet surface, temperature of the atmosphere. This is the surface that's emitting, so I want that temperature. And of course, we need to raise this to the 4th power. And we need to multiply by the factor of 4 for reasons we talked about before. Okay, so now I have I1 and I2, and now let's see if we can figure out I3. Well, what we argued before is that I3, that's the fraction, that's the amount of I2 that's being absorbed by the atmosphere, and that's controlled by the absorptivity A right there. So if you want to give that one a shot, go ahead. Okay, assuming you're back, then I think I will do it this way. I'm going to say that's equal to A, the absorptivity, times I2. Okay, so there we go. All right, and I can see that's good that it's a little bit less than I2. That's because A is only 0.7. And let's see, what about I4? If you want, go ahead and give this one a shot. All right, I think that's going to be equal to, it's going to be 1 minus the A or E, the absorptivity, and now that times I2. Okay, so that's that one. Now the last two fluxes that we have to worry about is I5 and I6. That's the gray body emission up and down from the atmosphere. If you want to give that one a shot, go ahead. Okay, I think what I need to do is start off with an equal sign as usual. And let's see, oh, well, we already wrote down the formula here. It's the emissivity times sigma of the atmosphere times 10 to the 4th times 4. So let's see, epsilon, that's that number right there, the emissivity, that's good, times, now we need to make sure we have the temperature of the atmosphere raised to the 4th, that's that number, okay, raised to the 4th, and epsilon times sigma, oh, I forgot sigma, okay, but I can just add it in here, times sigma, okay, and we need to multiply by 4, so there we go. And now what are we going to do for I6? Well, I6 is just the same as I5, so we can do it this way. I can just say that's equal to that value. Okay, now last little bit here is that we need to establish the balance, the radiative balance conditions, and one of them was this, that I've got it written down here, but we can look back at this picture. At the surface, it better be that I1 plus I5 equal I2. So, and what we need to do in Excel for this is enter that as in an equation that equals 0. So I'm going to say that that's what did we say? That's I1, okay, I1 plus and I5 minus I2, because that's what's coming off, and equals, that's what that formula is, and it's in the solver we're going to make this equal to 0. Now what about the imbalance in the atmosphere? Well, I think that means here, I think what's going in is I3 and what's going out is I5 and I6. If you want, go ahead and give that a shot. Okay, I think I need to say that is equal to the incoming I3 minus I5 and minus I6. And there we go. So you can see that these numbers that I've entered in do not produce a radiative balance. We've got imbalances at the surface and at the atmosphere. Obviously, if I changed, these numbers, I could, alter those numbers. But it's kind of a bother to change both the temperature of the planet, and the atmosphere. It's a lot easier to get Excel to do this for us. So let's do that. Okay. Now, what you want to do is reset all, if you've done this already, and let's see. What I want to do is I want to fix this imbalance at the surface. So our objective is to make that to a value of 0. And how are we going to do that? Well, we're going to tell Excel to vary 2 cells simultaneously. And the way we do that is I'm going to left click on this temperature, drag down to here, and now as you can see it thinks that it's going to change B6 and B7 in order to make this work. Now we not only want to make this imbalance 0, which is I've done here, the B15, that's the imbalance at the surface, but I also want to make the imbalance in the atmosphere 0, and the way you do that here in solvers, we add a constraint, and that constraint is this box right here. And what do we want to make it be? Well, we want it to be 0. Okay, so I'm going to say equals 0 there. And when you're done, you say OK. And hopefully that's good to go. I just said solve. Solver found a solution. That's good. Let's see, what did it get? Well, it produced 2 very small numbers, 10 to the minus 4 and 10 to the minus 8. That's pretty good. What did it find in terms of the temperatures? 283 and 238. And so those are our solutions for the isothermal atmosphere case with an emissivity or absorptivity of the atmosphere of 0.7.